Thank you. So, as Roman said, I'm going to present on competition and convergence in complementary contests. This is experimental work, and I would very much appreciate any feedback or questions people have, because I want to make it as good as possible. All right. So, let's start with a little bit of motivation. So, it's quite common that success in one contest can enhance the value of achieving success in other contests. For example, firms compete for both consumers and workers, and these things can be complementary. So for example, ride-sharing firms like Uber, they market themselves both to people who ride in their service, who are consumers, and to people who drive in their service, who are workers. And there's some kind of complementarity between these two marketing competitions, in the sense that having an additional rider is useful to the firm, especially when there are plenty of available drivers. And having an additional driver is useful to the firm, especially if there are a lot of people who want to ride in the ride-sharing service. So there's complementarity between these two inputs. Another important thing to notice about this situation is that the things they are competing over are divisible. A lot of times in work on contests, we imagine that the prizes that the contestants are competing over are indivisible. But in this case, like in this marketing competition for riders, the prizes are actually divisible. One firm doesn't necessarily get all of the riders, but they get some share of the overall riders in the market. It's also true that military factions often compete over complementary regions. So for example, a military faction might compete with another for control over some area of land, and they might simultaneously compete for control over the airspace above this land. And there's complementarity between these two, in the sense that controlling some area of land is more useful if you also control the airspace above it. And controlling some area of airspace is more useful to the extent that you control the land below it. And similarly, as before, this control is divisible. It's not always true that one faction has complete control over an area, but they can have some degree more or less control. So in a sense, we might say that that control is a divisible prize. It's also true that producers often compete for complementary inputs. People who produce lithium-ion batteries often need lithium and cobalt. These are two resources which are not terribly plentiful that are necessary to produce things like lithium-ion batteries, which are in high demand right now. And so producers might need to compete to control these inputs, and they are indeed complementary in the sense that they're both used for this very valuable purpose of producing lithium-ion batteries. Okay. So this paper falls into a broader literature which discusses complementarity in contests. For example, Kovanok in 2010 describes a weakest link contest. And this means a situation where there are attackers and defenders, and a defender needs to successfully defend all of their targets in order to be successful. So there's a kind of complementarity between these targets. Colmar and Romswinkel 2013 looks at complementarity between the efforts of team members. Deck et al. 2017 looks at majoritarian conflicts. These are like elections where the goal is to win the majority of the prizes. This paper is a little bit different in that it looks at divisible prizes and it looks at actual complementarity between these divisible prizes. So this is kind of like the examples we just discussed on the previous slide. So in particular, this paper is going to experimentally investigate conflicts where there are two agents and they compete in two complementary contests. Agent I is endowed with some amount, Wi, of competitive resources. If we're thinking about a military contest, this might be like soldiers or planes, right? If we think about a marketing contest, this might be like advertisements. And the idea is that these agents have a certain budget that they're going to allocate between these two contests. And the real question to them is, how much do I allocate to one versus how much am I going to allocate to the other? So some notation here. We use XIB to denote the quantity of competitive resources that agent I allocates to contest B, where B is either 1 or 2. So we say that XI1 plus XI2 equals WI. Agent I allocates all of her resources either to contest 1 or to contest 2. So let's think for a moment about how these allocations determine each agent's share of the prizes. There are 2 prizes, one for each contest, and we use YIB to denote agent I's share of prize B. We can see that YIB is increasing. Agent I's share of prize B increases as agent I allocates more resources to contest B. In the sense, if I put more effort into marketing my ride-sharing service to riders, then you expect me to get a larger share of the available riders in the market. On the other hand, this share of prize B is decreasing in the amount of resources that the other agent allocates to this contest B. In other words, if my opponent allocates more resources to marketing to consumers, then we expect them to get a larger share of the consumers and me to get a smaller share of the consumers. We also have this parameter A here. A denotes the level of competitiveness in this conflict. So in the limit, as A goes to infinity, this becomes an all-pay auction, where the agent who allocates even slightly more resources to the contest gets the entirety of the prize. On the other hand, as A gets very, very small, as it converges to 0, then we would get a contest where the prize is equally divided between the 2 agents, regardless of how much they allocate. All right. So remember that the whole idea here is that there's complementarity between these 2 prices. And in particular, we look at the case of constant elasticity of payoffs with respect to shares of each prize. So here, pi I denotes the payoff to agent I. And as we said earlier, YIB denotes agent I's share of prize B. We use VB to note the value of prize B. And we have this parameter C. C denotes the level of complementarity between the prizes. So when C goes to infinity in the limit, then we would have the case of perfect complements, where each prize is only useful in combination with the value of the other prize. It's useless on its own. So in a sense, the payoff would be based on the minimum of the 2 prize shares. On the other hand, when C goes to 0 in the limit, then we would get the Cobb-Douglas case, which is sort of on the boundary between complements and substitutes. All right. So that's enough about the theory of the setup here. Let's think for a moment about the predictions. So one important prediction is that for all of these parameters, we are always going to have a unique Nash equilibrium. And this unique Nash equilibrium is only going to depend on the endowments that each agent receives and the valuations that agents have for these particular prices. In particular, this means they're not going to depend on the level of complementarity between the prices. They're not going to depend on the level of competitiveness. So here in equilibrium, in the unique Nash equilibrium, the allocation of agent I to contest B, we can see depends only on agent I's endowment and the valuation of contest B and the valuation of the other contest. So it's really missing these parameters A and C, which was a little bit surprising to me. When I noticed this, intuitively, I had expected the level of complementarity or the level of competitiveness to influence this allocation, but in fact, it does not. Let's try to get a little bit of intuition for this phenomenon. So here we can see the best response correspondences for each agent. In the case where the level of competitiveness is 1, the level of complementarity is 1. Each agent is endowed with 100 units of competitive resources. The first contest has a prize with value 2, and the second contest has a prize with value 8. Here we can see that the Nash equilibrium involves each agent allocating 20% of their resources to contest 1, which makes sense because contest 1 has sort of 2 out of the total 10 valuation. We can see that the best response correspondences are sort of S-shaped here. Now let's look and see what changes when we change the level of competitiveness from 1 to 8. The first thing that should pop out to you is that the equilibrium does not change. The equilibrium allocation to each contest is completely unaffected when we change the contest from a sort of mildly competitive contest to this is a very competitive contest. In conventional contests, the sort of conventional setup for these type of contests without complementarity, this level of competitiveness would be so high that a pure strategy equilibrium wouldn't even exist. We would be in the realm of mixed strategy equilibria. But in this case, in this particular case of complementarity, we sustain a pure strategy equilibrium even at this very high level of competitiveness. And again, it doesn't change as the contest becomes more competitive. What does change is the shape of this best response correspondence. It's still S-shaped, but it's much closer to being linear. And that's the key intuition for what we're going to explore in this experiment. So in particular, our sort of behavioral model that we're going to be examining is what we call the myopic best response dynamic. And this is probably something you've seen before. It's a model that describes agents who best respond to what they observed in the previous period. So here, XIT is the allocation selected by agent I in period T. And this model says that agent I selects something that maximizes the payoff she would have received in the previous period given what her opponent did in the previous period. So this is, again, you might hear this sometimes called the Cournot dynamic or lots of other things. And it's been around for a long time. It's nothing new. Here we can see the predictions of the myopic best response dynamic. And we can see the predictions again in this case where the level of complementarity is 1. Each agent is endowed with 100 units of competitive resources. And we'll look at the case where the first prize has a value of 2 and the second prize has a value of 8. The difference here between these two lines here has to do with the level of competitiveness. So these blue circles denote the path of the best response dynamic under this high competitive regime where A equals 8, and these green diamonds denote the path of the best response dynamic in this low competitiveness regime where A is equal to 1. And what we notice is that we find much faster convergence to the Nash equilibrium prediction in the case where the contest is less competitive, which again, to me, was a little bit surprising. Intuitively, you might expect to see faster convergence under more competitive contests, but we actually see the opposite, at least in this prediction from the best response dynamic. So our experimental design is 2 by 2. We have 2 treatment conditions. One treatment condition looks at the level of competition in the contest, and the other treatment condition looks at the valuations of the prizes. So first, let's look at our competition treatment condition. We have 2 cases. In the more competitive case, we have this one where A is equal to 8, and in this less competitive case, we have A equal to 1, and this corresponds to the graphs that we were looking at earlier.
Daniel, I'm so sorry for interrupting. You have about 10 minutes left.
Thank you. So the other treatment condition looks at the valuations of the 2 prizes, the 2 prizes, 1 for each contest. In valuation 1, we have the first contest with a prize that has a value of 8, the second contest with a prize that has a value of 2. Under the second valuation treatment, we have exactly the opposite. The first contest, that prize has a valuation of 2, and the second contest has a prize with valuation 8. In all of our treatments, each agent is endowed with 100 units of competitive resources, and the level of complementarity is equal to 1. So each session had exactly 20 subjects, and these subjects were divided into 10 pairs of 2 subjects each. We used fixed matching, so this means that each pair remained together for the entire session. Members of one pair never interacted with members of another pair. So you were competing against the same opponent again and again in each period. This is, first of all, what is described by the best response dynamic, so it helps us to be consistent with the theory that we're trying to test. And it also helps prevent sort of correlation between these different behaviors. It gives us more statistical power. Each session consisted of 100 identical periods, and during each period, each agent allocated 100 units between two battlefields. At the end of each period, each subject received feedback about the strategies and payoffs. So here you can see, for example, that the subject can see that in the previous period, they allocated 67.2 to battlefield 1 and 32.8 to battlefield 2. We called these contests battlefields in the experimental instructions, and we can see their payoffs, the other subjects' strategies, the other subjects' payoffs. We can see what they're planning so far to allocate in this period, and we can see how much time is left for them to make their decision in this period. And this graph illustrates, again, the same information, but just graphically. Their payoffs and their strategies last period, and the strategies that they're planning for this period. But of course, they don't know what payoffs they'll earn in this period, because that depends on the strategy selected by their opponent. And that information is not given to them, of course. So we have two groups of hypotheses here, one from Nash equilibrium and one from the best response dynamic. Nash equilibrium predicts that we should see more allocation to contest 1 under evaluation 1 and more allocation to contest 2 under evaluation 2. Whereas the best response dynamic predicts faster convergence in less competitive conflicts and slower convergence in more competitive conflicts. Now let's take a look at what we actually observe in the experiment. I'm sure this is the part we all actually want to see. So, first of all, we did indeed observe convergence to this equilibrium where agents allocate 80% of their resources to contest 1 in evaluation 1. And we observed convergence to this equilibrium where agents allocate 20% of their resources to contest 1 under evaluation 2. This convergence is, of course, imperfect, but in the long run, it gets reasonably close. What's very interesting to me, at least, is that this treatment here and this treatment here see much faster convergence to equilibrium than these two treatments. And we can notice that, as predicted by the best response dynamic, the faster convergence is in the treatments with less competition, that have sort of weaker competition between the agents. So let's look at some formal hypothesis testing here. So this compares the allocation to contest 1 under evaluation 1 and evaluation 2. Our unit of observation is one fixed matching pair. And again, we do this to avoid autocorrelation over time. And these fixed matching pairs never interact with one another, so they are effectively independent. The number of observations here is 80. That's 8 sessions times 10 pairs per session. And we find that this difference is statistically significant, both with a t-test and a non-parametric ring sum test at the 1% level. Now let's take a look at the deviation from equilibrium by period. So again, we're just now looking at how far were subjects on average from the equilibrium prediction by period within a session. And we can see that the less competitive treatment is consistently lower over all periods, and the more competitive treatment is consistently farther from equilibrium over all treatments, although both of them are converging towards equilibrium. And who knows what would happen given more time. But we do give them 100 periods, so we hope we give them enough time to get the feel for it. So we have a hypothesis test looking at this effect. Here we see that subjects are significantly closer to equilibrium under less competitive conflicts and significantly farther away from equilibrium under more competitive conflicts. And again, the unit of observation is one fixed matching pair. And this difference is statistically significant both for the parametric t-test and the rank sum test at the 1% level. So in conclusion, what did we find here? We found that convergence to equilibrium is actually faster in less competitive conflicts, which is interesting. I think the even more interesting thing about this is that these results are consistent with the predictions of this very simple adaptive myopic best response dynamic. And this suggests that similar adaptive models may be useful to economists in answering questions like, how long is the long run? You know, Keynes famously said that in the long run, we're all dead. And when he talked about the long run, he was referring to reaching this idea of equilibrium. But whether or not in the long run we're all dead depends on how long that long run is. It depends on how long does it take us to reach something that approximates equilibrium predictions. And that's the kind of question that we'd like to be able to answer, and adaptive models may be useful in helping us find those answers. Of course, more research will be needed to investigate the generality and the external validity of these results. Thank you. Are there any questions?
Excellent. Thank you so much, Daniel. We have about 3 minutes for extra questions. If you don't mind, I'll start with mine.
Please.
So my question is just in terms of alternative possible models for the convergence of behavior to equilibrium. Have you thought of those, or did you just look at the simple Cournot one period back response? I'm just kind of curious, you know, because you don't have a baseline versus, you know, other models to compare. So that's why I'm curious.
Right. So why did we look at this very simple adaptive model? Well, I started by looking at some more sophisticated learning models that gave very similar results. And so I sort of eliminated parts from these models as far as I could. And what I found is the results were basically the same for all of them. So if you look at a logit response or some kind of weighted fictitious play or a lot of other similar adaptive models, you're getting, although different in shape, this consistent result that you get faster convergence under less competitive models. And so for simplicity, I focus here in this presentation on the simplest of these models, but it's actually quite consistent.
But in the paper, you have all of those, right? Is that?
I don't have a working paper for this yet. It's still fairly recent, but I do intend to show multiple learning models in the paper, yes.
Okay, cool. Thank you. Any other questions, please? We have about 20 people. Please, guys, go ahead. Unmute yourself and.
Can we just speak up?
Please, please.
Yeah. How's it going?
Hi, Daniel. Hi,
Hello,
Roman.
Tim.
Interesting talk. If I must understand correctly, the feedback, well, the decision screen that the subjects had displayed, that's a counterfactual payoff
in the previous
projection
period, yes.
from the previous period. So that
Exactly.
would seem to encourage the kind of Cournot type belief formation. I'm wondering, that's apparently a deliberate design choice.
That's correct. You know, and one big question here is how well would these results hold up if we took away that feedback? Certainly, we know that subjects are not good at math, and what we're doing here is we're doing their math for them. It's a good question if we took away that crutch, that ability to sort of do the calculations for them. Again, even without the line, we've given them all the information to calculate the line, but they might not be able to calculate it unless we did it for them. And it might change the results, and that's a really good question, and I'd love to actually run a follow-up to check that as well.
Yeah, interesting.
Excellent. Well, thank you so much, Daniel. So the next speaker is going to be Elaine Reeve from University of Arizona. Please go ahead. You have about 25 minutes. I'll give you a warning 10 minutes before your time runs out.
Okay. So can everyone see my screen? Well, yeah. Awesome. So hi everyone, I am Elaine Ree. I am a fourth year PhD student at University of Arizona. Today I'm going to introduce my paper, Is the Gender Difference in Competitive Behavior History Dependent? So I have 4 research questions. The first one is whether fairness history with a competitor explains the willingness to enter a tournament at an individual level. So if someone was unfair to me, do I want to compete with that competitor more or less? That is the first question. The second question is whether fairness intentions matter. So if someone was unfair to me by accident or by choice, does that actually make a difference in my competitive behavior? That's the second question. The third question is whether emotions affect one's competitiveness. So here I'm looking at, is there a certain history that triggers a certain emotion that makes one want to enter tournaments more or less? And the last question is if there is a gender difference in the questions above. So the first thing that I do in my paper is that I study how fair and unfair history caused by a competitor influence one's winner-take-all tournament entry. According to the inequity aversion models, the person is supposed to enter the tournament after an unfair event to even out the distributive consequences. In the reciprocity models, it's also predicted that a person would enter a tournament after an unfair event, but now the motivation is different. It's not to even out the distributive consequences, it is to punish that person who caused the unfair event. The second thing I do is I'm looking at if the intention of the fair or unfair history matters. According to the inequity aversion models, no, it's not supposed to matter that much. Only distributive consequences matter. However, in reciprocity models, fairness intentions have a major behavior role. So depending on the intentions, the behaviors are supposed to change. In experiments, there have been support for both approaches. So when it comes to competitive behavior, it is not obvious which way it's supposed to go. I also study how emotions affect competitive behavior. In Lung and Nozer's paper, fair, happiness, anger, and surprise is positively correlated with risk aversion. Lerner and Keltner show that fear leads to pessimistic risk assessments and anger to optimistic ones. So it has been shown in many papers that emotions actually affect one's behavior, but it hasn't been shown how is it affecting competitive behavior, so that's what I'm doing right now. Hopefully at the end, I will be able to give a new perspective on the labor market outcome. Bertrand and Hollick shown that in the US, women account for only 2.5% of the 5 highest paid executives. Netherlands and Westerland suggests that women shy away from competition more than men do. So maybe this is why women are not well represented in the labor market. Over here, I study, is it that something happened before is making women to shy away from competition? Is there an unfair history behind that, that women are shying away from competition more than men do? So here's the preview of my results. Unfair history with intentions matter. Both men and women enter tournaments more when the competitor was unfair by choice. And actually, men react more sensitively than women do in this case. Unfair history without intentions don't really matter. Both men and women do not enter tournament more when unfair history happened by accident. So I do lab experiments to see how the research, so that I can answer the research questions. And I have 2 treatments. The first is the dictator game treatment, and the other one is random treatment. Both of the treatments consist of 4 parts, practice part, part A, B, and C. Part A is the part that I'm actually interested in. Part A is how I see like history is affecting competitive behavior. Part B and C are just for controls. In those parts, I get the distributional preferences and risk attitudes of the subjects. So the practice part is literally a practice part for the subjects to familiarize themselves with the task. It is based on Netherlands, Westerland. So the subjects had to do an addition exercise. They had to add up sets of 5 2-digit numbers for 3 minutes. They were not allowed to use calculators, but scratch papers were given to use. At the end of the practice part, subjects got a feedback on how many questions they got it correct, but they didn't get any feedback on the other participants' performance. And also, this was the only part in the whole experiment that they got some sort of feedback on their performance. Part A, so this is the important part in my experiments. The subjects were randomly matched in groups. In each group, there were 2 people. One was a dictator and the other one was a scheme chooser. The people were rematched every period, and the role did not change throughout the experiment. So a dictator was matched with a new scheme chooser every single period and vice versa. Part A was repeated 4 times. I'm going to call this 4 periods. And part A was video recorded the whole time so that I can analyze the emotions of the subjects using something called face reader. The emotions that I was able to analyze was neutral, happy, sad, scared, surprised, disgust, and angry. So part A, stage 1, this is when the history happens. I make the subjects do a dictator minigame. So the dictators in each group had to choose how to allocate $16 with a matched scheme chooser. The dictator had 2 options. One was to grab. If the dictator grabbed, he got the whole $16 and the scheme chooser got nothing. So this was an unfair event for the scheme chooser. Whereas when the dictator shared, they equally got $8. So this was more of a fair event for the scheme chooser. Note that when I say fair over here, it doesn't mean fair in the way that it's reasonable. It's more something like equality. So at the second stage, this is when the scheme chooser choose to enter a tournament or not. I use strategy method to do that. So the scheme choosers look at a screen that only shows the total amount you and the other player had to share is 16. Let's say the other player offered you 0, nothing, and took the whole $16. So they look at that for 20 seconds, so they have enough time to read that and express the emotions they have in front of the camera. And then they move to another page that they are allowed to choose a peace raid or tournament with a matched dictator. I do the same thing for the share case. Instead, the page now shows the total amount you and the other player had to share is 16. Let's say the other player offered you 8.5. So they look at that for 20 seconds and then move on to a page where they can choose tournament or peace rate mode with the dictator. So what happens when the scheme chooser chooses peace rate or tournament? Well, when the scheme chooser chooses peace rate, it's an independent payment. So both the dictator, the matched dictator, and the scheme chooser gets $1 per correct problem. However, when the scheme chooser chooses tournament, now the payment is in comparison. So between the 2 group members, whoever gets more questions correct is the winner, and that winner got $2 per correct problem. However, the loser got nothing. The last stage of part A is guessing. So all part subjects were asked to guess their performance and the match player's performance. By doing that, I was able to get 2 measures, overconfidence level and confidence level. In part B, this is the part that I got the distributional preferences for the scheme choosers. It has been shown in the Belmar et al. Paper that own distributional preferences and others' intentions are determinants of the view of fairness. So I have to control the distributional preferences. And to do that, I used Belafutis, Kirschbaumer, and Sutter method. The scheme choosers are asked to pick one between the binary choices for each task. They decide how much to give themselves and how much to give the matched dictator. And by looking at these choices, I was able to get the distributional preferences. The last part, part C. So I have 2 stages. In both stages, I use multiple price lists. However, I use different numerical values for each stage. The duplicate MPLs are placed in different parts of the experiment to alleviate the tendency for consistency of responses. So this is how the dictator game treatment worked. The scroll bar is the time that I actually gave them the instructions. So the experiment started with the general instructions, and I gave them a quiz about the general instructions. In my data, I only used people who got more than 95% correct. And then after that, I make the subjects do the MPL with a $12 gamble, and then do the addition exercise, which was just a practice. Part A was done 4 times in the order of dictator minigame, choosing tournament entry, doing the addition exercise, and guessing performances. So after that was done, the distributional preference was, that part was done, and then the last MPL with $8 gamble was done. The experiment ended with a short questionnaire. So this is the dictator game treatment. Remember, I also have a random treatment. So in the random treatment, what is happening is that only part A, stage 1, is different. The dictators are not making their decisions anymore. The computer is randomly drawing the decisions for the dictator. So in the dictator game treatment, if an unfair event happened that is by choice of the dictator, However, in the random treatment, if an unfair event or a fair event happened, that was not by the choice of the dictator, it was just by accident. It's just the computer's random decision. So here is a result of my summary statistic of my paper. This is the average tournament entry percentage. So if you see in the case over here, males and females tournament entry decision, females enter tournaments less than male do in general. And also one pattern that we see is that no matter what treatment it is, and no matter the gender, when the unfair history happens, people enter tournament more compared to the fair history. Also, another thing we see is that when an unfair history happens, both men and women enter tournament more under the dictator game treatment compared to the random treatment. So here is my regression model. I use ORIV, obviously related instrument variable, from this paper over here. So I have two risk attitude measures from the two MPLs. I use one risk attitude measure as an instrument variable for the other one, and also do it the other way around. Over here, I denotes the scheme chooser, J denotes the match dictator, T denotes the period. YIT is the outcome variable, such as tournament entry decisions, and also performance. XIT is the control variable that includes distributional preferences, confidence level, emotions, time trend, etc. MUI is a subject random effect. I use the panel linear probability model to regress this for the tournament entry decisions. I also do a probant model in my paper, but for the time's sake, I'm just going to introduce the linear probability models over here. For the performance regression, I use the panel Tobit model. So this is what happens when I control for distributional preferences, confidence level, and risk attitude. In the dictator game treatment, unfair history effect exists. People enter tournament more after an unfair history than after a fair history. In the random treatment, however, we don't see that unfair history effect. So by comparing the dictator game and the random treatment, we can see that intentions actually make people behave a little bit different. Also, in the dictator game treatment, there is a gender gap in unfair history effect. Men enter tournament more than women do after an unfair history. In fact, that gap is 23 percentage points. In the random treatment, there is no gender gap in general. So now I control for emotions as well. I control for distributional preferences, confidence level, risk attitude, and emotions. And this is what it happens. Unfair history effect still exists in the dictator game treatment. Men enter 50% point more, women enter 29% point more after an unfair history compared to a fair history. Gender gap and unfair history effects still exist in the dictator game treatment. So men have a greater unfair history effect than women do. That gap is 21% point. So if you remember, before I controlled for the emotions, the gap was 24% point, and now it is 21% point. So I'm suggesting that emotions partially explain this sensitivity difference in unfair history. In the random treatment, we do see some evidence that women enter tournament less than men, regardless of history. So women enter tournament less than men do, no matter what happened in the random treatment. If we look at emotions, surprise has a significant positive effect in the dictator game treatment. So the story behind this, I suggest, is that people expect others to be nice or fair to them. It's been shown in Bill Maher et al. Paper that negative expectation violation can increase the tendency to penalize a violator in ultimatum games. So I'm saying that people expect others to be fair to them, but when they're unfair to them, that is a negative expectation violation. So just like in ultimatum games, they want to penalize the person who made that negative expectation violation. And in this case, they're using tournament as a way to penalize them. So if we look at performances, unfair history affects women's performance negatively and does not have effect on men's over here. Also, this unfair history effect on women's performance is bigger in the dictator game treatment compared to the random treatment. So when intentions are really there, unfair history really makes women's perform worse, whereas when the intentions aren't there, it has a little bit less effect. Also, if you look at over here, in both cases, in both treatments, entering tournaments is not beneficial to women regardless of history. So in conclusion, I do a lab experiment to see how history affects one's competitive behavior. In the dictator game treatment, unfair history makes one want to compete more. In the random treatment, there isn't really an unfair history effect. Gender difference in this, the dictator game treatment and random treatment are slightly different. In the dictator game treatment, men's behavior is more sensitive to unfair history than women's. Emotions partially explain this. In the random treatment, we've seen a gender difference in the way that men enter tournament more than women in general. Performance-wise, unfair history affects women's performance negatively, but does not affect men's performance. So the takeaway from my paper would be, unfair history can exacerbate the gender gap in competitive behavior. It has been shown in many papers that women just don't enter competition as much as men do, and I'm suggesting history can actually make that gap even bigger. Women are not well represented in competitive jobs, and that could be because considering a competitor has been unfair or unkind, women may not enter the competition at the same rate as male competitors do, and if they do, they perform worse than men. If the behavior that we've seen in the lab also occurs outside of the lab, like these two papers show that the competitive behavior in the labs are actually related to the behaviors outside of the lab. When women encounter unfair events like gender discrimination, it can make them compete even less and perform worse. Thank you.
Excellent. Thank you so much. This is very interesting. So we have about 5 minutes for Q&A. Please go ahead. You'll need to unmute yourself and then just go ahead and ask questions.
Hi, Elaine.
Hi.
I had a question about part of the design. My guess based on your scrolls for the instructions was that they didn't know anything about the tournament or piece rate choice in the first game, but in subsequent games they presumably they knew that the dictator decision would perhaps influence the choice of incentive scheme afterwards.
So
is that right?
Over here in the practice part, when they do the addition exercise, this wasn't incentivized. It wasn't a tournament or a piece rate. It was just a practice. And then after over here, after doing the dictator game and the strategy method, when they do the addition exercise, it depends on what the scheme chooser chose.
Okay, so I mean between stage 1 and stage 2 of part A.
Yes.
Because my question is about as a dictator, oh, because they do the strategy method, it doesn't matter then. And my question would have been, as a dictator, should I choose to take everything if I think that I'm going to lose in the tournament stage?
Oh, so to prevent that a little bit, I don't pay all of the stages in the experiment. I pay, I randomly choose a stage that I'm going to pay. The stages are this first MPL, the second MPL, the distributional preferences, dictator game, and the stage 2. So they know that in the general instructions that I told them, only this can count, or only this can count, or only the other ones can count. So that I kind of cut that income effect a little bit.
Yeah, because the only concern then would be that maybe you pick up people entering the tournament less so because of emotions and more because they're taking it as a signal, or they would take it as a signal that it's a weaker or a perceived weaker dictator who's taking everything. But I think that's a good answer to prevent anything like that.
Thank you.
Okay, other questions, please.
One question I had, how did the decisions of the dictators change in later periods versus earlier periods?
So interestingly enough, the dictators didn't really change their decision that much when I looked at the data. So I repeated 4 times. Sometimes they change it like only one period, but usually most of the time they stick to the decision they made it at the first time.
Understood. And what about tournament entry? Do you see something similar there?
Yes, tournament entry wise too. I use strategy method, and most of the time the scheme choosers stick to their decision they made at the first time. But sometimes they change in one period, but it's not like 2 periods I do this, 2 periods I do like completely something different. It's not like that.
Makes sense. Thank you.
Thank you.
Okay, one more question. It's going to be the last question if we have. Well, if not, thank you, Elaine. It was a really good presentation.
Thank you.
The next presenter is going to be Jian Song from George Mason University. She's going to talk about costly weighting in dynamic contests. Okay, Jian, go ahead. I will, again, when 10 minutes is left, I will sort of let you know about that. Rather than that, it's all yours.
I'm just mute myself, so sorry. Okay, so can now everyone see my screen? Okay, perfect. So good morning, everyone. Thanks for coming here, and thanks for inviting me to join this session. My name is Jian, currently a PhD candidate at George Mason. And today I will talk about the paper co-authored with my advisor, Daniel Hauser, named Weighting in Contest, Theory and Experiment. So for our paper, we investigate the dynamic contest. And the dynamic contest means the competition will last for multiple periods. And basically, we usually use the wall of attrition to model such dynamic contest. So for the original wall of attrition model, the players will compete in pairs. And before the competition starts, they will know their strengths privately. And based on their strength level, they will decide when to exit the game. And the weighting is costly in wall of attrition. The longer time you wait, the higher weighting cost you need to pay for it. And the contest will finish as soon as at least one player exits the game. Therefore, such wall of attrition will always end with only one result, that is escape. So if we want to apply the wall of attrition model into the real world conflict, so what problems may occur? So one major problems may be actually in our real world conflicts, players can actively fight with their opponents. So for example, like the military war or like the worker union strike. So in order to fill the gap between the wall of attrition model and the real world scenario, in our study, we are building from the Lewis model, extend the wall of attrition by allow players to choose to fight with their opponents. However, that fighting is costly, so actually no one would love to win the contest with such costly battle. So in order to measure such a scenario, we assume that players actually can win the contest, plus a positive deterrence value if their opponents flee earlier. So we also assume that weighting is very costly in our dynamic contest. And another difference, like the Lewis model, in our setting, we restrict players by only allowing them to fight in the last periods, because we believe by this assumption, we can measure the most natural environment, like Actually, no one loves a costly battle, so players usually leave some time to their opponents in order to give them chance to escape. So based on our model, we pay special interest to investigate how your waiting cost and the deterrence value can jointly affect the type of equilibrium in our dynamic contest. And based on our model, we then conduct experiment to verify the theoretical findings. So let's see the motivation for our study. We believe by incorporating the battle auction and then assume like the waiting is costly can allow us to model a wider variety of the dynamic contest. Specifically, it can help us to answer the following 3 questions. And the first one is why in our reality, some contests end with battles, while others can end with escape. For example, in the military war, it sometimes ends with 2 sides fight with each other, while others it will end with one side like surrender. And the second question is why like some players can wait for longer times and then to take actions. One example is the 2019 General Motors strike. Actually, it took both sides around 10 years to negotiate before that strike outbreak. And the last question is whether the waiting cost and the deterrence value can be effectively to eliminate the weaker players from the contest. If that is true, then we can see by manipulating the waiting cost and deterrence value, we can then reduce the battle rates and therefore can lead a more peaceful results. So here is the main results of our study. By using our model, we found like the ratio of waiting cost to the deterrence value actually is a key factor to determine the type of equilibrium. And specifically, when holding other factors are fixed, as your waiting costs increase, less battle occur, and the weaker players are more likely to flee firstly, which is quite intuitively. And the experimental results confirm the qualitative feature of this model. However, quantitatively, we found like as waiting costs increase, the difference on the fraction that weaker players flee firstly and the willingness to fight will get smaller when compared with theoretical predict. So now let's turn to see the model we investigate in our study. In our model, we study the 3-period dynamic contest. And before the contest starts, players will privately know their strengths, and the distribution of their strengths is a common knowledge. And in the first 2 periods, players will decide whether to wait or flee during the game. And at the last period, they will decide whether to fight or flee the contest. So in the first period, if both 2 players decide to wait, then the game will proceed to next period. And if at least 1 player decides to flee, then the game will end immediately with the result of an escape. So as for the payment, the one who chooses to flee will get nothing, and the one who chooses not to flee the game first will get the winning prize, and then he will get the positive deterrence value, which is K. And if both players decide to flee at the same time, then they will split the winning prize and the deterrence value. So same thing for the next period. If both 2 players decide to wait, then the game will proceed to the last period. If at least 1 chooses to flee, then the game will end at the 2nd period with a result of escape. The one who chooses to flee will get nothing. Also, she needs to pay the waiting cost. The one who chooses not to flee will win the competition with the winning prize and the deterrence value. Also need to pay the waiting cost. And if both of them choose to flee, they will split the winning prize and the deterrence value. So if the game proceeds to the last period, the choice will be different. Players then will decide whether to fight or flee. If both of them choose to fight, then the game will end with battle. If 1 chooses fight, 1 chooses flee, then the game has 50% chance to end with escape and another 50% chance to end with battle. And if both choose to flee, then the game will end with escape for sure. As for the payment, if the game ends with a battle, then your payment is totally decided by your fighting strengths. The one who has higher strengths will win the battle for sure, and she will get the winning prize, also pay the waiting cost. And the one who has lower fighting strengths will lose that competition. She will firstly need to pay the losing price, which is negative VL, and also she need to pay the waiting cost. So if the game ends with an escape, then the same payment structure as before, like the one who chooses to flee will get nothing, and the one who chooses not to flee will get the winning price and deterrence value. And if both choose to flee, then they will split the winning price and deterrence value. Also, they all need to pay the waiting cost. So that is the model we investigated in our game. And I just give the mathematical derivation on the equilibrium, on how we get the equilibrium. I just show you like the intuitive results. So we look for the pure strategy based in equilibrium in our model, and we derive the equilibrium under the assumption that player have sharehold strategy. Like if your fighting strength is above that sharehold, you will choose to fight. And if you fighting strength below that sharehold, you will choose to flee. So first, let's consider the case when your waiting cost is very low. If your waiting cost is very low, intuitively, all the players would love to stay in the game until the last period. Therefore, they can give their opponents chance to escape, and they can obtain the benefits of the positive deterrence value. So we refer such case as the waiting equilibrium, and it can be characterized by one sharehold value, which I use A bar to represent. So if your fighting strength above that A bar, you will choose to fight at the last period. And if you below that A bar, you will decide to flee at the last period. So what if the waiting cost becomes a little bit higher? So in that case, there will be a fraction of the player who has lower fighting strength. They will decide to flee immediately at the game. Therefore, they can avoid paying for the waiting cost. So we refer such equilibrium as the jump equilibrium. And it can be characterized by two sharehold value, A1 bar and A2 bar. So if your fighting strength above the A2 bar, then you will decide to fight. Otherwise, you will decide to flee. So if the waiting cost becomes even larger, then what happens? So if waiting costs become even higher, then a fraction of player among this area will decide to flee a little bit earlier. Therefore, they can avoid paying the more waiting cost. So we refer such equilibrium as gradual equilibrium. In that case, the players will flee gradually during the game. And it can be characterized by two sharehold value. And if you're fighting a three sharehold value, and if your fighting strength is above that A3, you need to decide to fight at the last. Otherwise, you will choose to flee during the game. So here I show you the equilibrium predictions when the winning price VH equals to the losing price VL equals to 100. And you can see the type of equilibrium is decided by both deterrence value K and your waiting cost C. Specifically, if we let K, the deterrence value, equals to VH equals VL equals 100, that is this line, these three red points will represent three different equilibrium, which are the treatment in our experiment. So in our experiment, we have three different treatments, which varied by the waiting cost. So C equals 5 will represent the waiting equilibrium case. In that case, theoretical predict all the players would love to stay until the last period. And C equals 20 will represent the jump equilibrium. In that case, there will be a fraction of players would love to leave immediately, while others would love to stay till the last period. And C equals 40 will represent the gradual equilibrium. In such case, player will flee gradually during the competition. And the predicted fraction that player choose to fight or flee in each period are shown as this figure below. As we can see, as your waiting costs increase, the fraction that subjects choose to fight will decrease gradually. And also, as your waiting costs increase, more and more players would love to flee before the end game, which are the main qualitative hypotheses in our study. So the main qualitative hypotheses in our study are these two. And the first one is the frequency of battle will decrease as your waiting costs increase. And the second one is there will be more weaker players decide to flee firstly as your waiting costs increase. If that is true, then it means like the waiting cost and your deterrence value can be effectively to for select the weaker player, to identify the weaker player from our competition. So now let's look at our experimental results here. So here I use the black solid line to represent the experimental result and the gray dashed line to represent our theoretical predictions. So as for the frequency of battle, we can see our experimental results will quite follow the qualitative predictions of theoretical predictions. That is, as your waiting costs increase, there will be the fraction of the frequency of battles will decrease. However, as your waiting cost becomes higher, that is from 20 to from 40, you can see the difference between the frequency of battle is much lower than what theory predicted. What's more, when the C equals 40, that is when your waiting cost is very high, the actual frequency of battle is higher than our theoretical predicted. The same thing happened when we consider the fraction that weaker player would flee firstly in our game. Same as the theoretical prediction, as your waiting costs increase, more weaker player would love to flee firstly. However, as your waiting cost becomes larger, then the difference between the treatment, like the difference between C40 and C20, is much lower than what theory predicted. And what's more, when we see the waiting cost equals 40, the actual fraction that weaker player would flee firstly is lower than what theory predicted. So based on this finding, we see like when the waiting cost gets larger, the treatment difference actually gets shrinks. And to get a further illustration, we then use a graph search to estimate each individual's cutoff strategy. And here is the results of our individual cutoff estimate. Here's E1, and E1 means if your this E1 will show you if your ability, if your strength is below E1, then you will decide to flee immediately. And that E2 shows you if your ability above that E2, you will decide to fight at the last of period. And if the point lands on the if your point stay on the line where E1 equals E2, which represent your strategy is bifurcate, like you either decide to flee immediately or decide to wait until the last period, then fight. So we can see like as your waiting costs increase, more and more subjects will stay on the line where E1 equals E2. That means as waiting costs increase, the player's action will more bifurcate. They either flee immediately or wait until the last period to fight, which actually is a contradict to our gradual equilibrium predictions. So to investigate why such a contradiction happens, one possible explanation we have considered so far is about like players may fall into the sunk cost fallacy. Like they treated their waiting cost as the sunk cost. Once they pay for it, once they pay very high sunk cost, it is hardly for them to leave during the middle of the game. So they would love to stay for the longer time and to fight, seeing whether they can win that contest. So basically that is what we've done so far. So we're building from the Loomis model, extend the wall of attrition by allow player to actively raise battle to their opponents at a certain period of contest. And also we further assume the waiting cost is costly. And our model shows that the ratio of waiting cost to the deterrence value is a key determinant for the type of equilibrium. And we conduct laboratory experiment with the three treatments that differed in waiting cost. And the experimental results will confirm our qualitative predictions. However, as your waiting cost increase, the treatment difference gets shrinks. So our and we think that may be caused by the sunk cost fallacy. And our experimental results shows that when your waiting cost gets larger enough, then the policymaker may fail to significantly alter the frequency of battle or the duration of conflicts by simply adjusting your waiting cost. So how to effectively lessen the such sunk cost effect in real world conflicts can be one direction for our follow-up studies. So, okay, that is all for our study. So thanks for your attention.
Wonderful, thank you so much. So we have some time for question and answers. Please go ahead. If you have a question, just unmute yourself, and I'm sure John will be happy to answer it.
One question, Zhang. I understand that some of your treatment effects were milder than predicted by equilibrium.
Mm-hmm.
Do you know if that result is consistent with either risk aversion or quantum response equilibrium?
Yes, actually we do some like regression analysis. In our experiment, like after they finish this computation, we do the risk or aversion test, loss aversion test to see whether your risk attitude or loss aversion attitude affect your behavior. And we found that actually risk aversion doesn't have significant impact on your decision. And the loss aversion matters, however, just a little bit. Yeah.
I mean, on the theory side, if you incorporate risk aversion into your model, do your predicted treatment effects become more mild?
Yes, that is a good question. Actually, we do the extension, incorporate the loss aversion into our model. And we found that yes, by including the loss aversion, the model can predict your the experiment results better. However, there is still significant difference between the theory predicted.
I see. One potential avenue to look at in that case to explain the remaining differences might be something like quantum response equilibrium, perhaps the presence of some kind of behavioral noise.
Mm-hmm. Yeah. Thank you. That is a great suggestion. We'll definitely go back to seeing whether the QRE model can predict better.
Thank you.
Yeah, thank you.
Wonderful. Anybody else? So we still have a couple minutes for Q&A.
Yeah, if no questions so far, like I'm willing to like switch to Sherman and you can start. And I'm willing to talk like after the session.
Wonderful, thank you. So I'll be the last presenter today. Please, because I do not have control over this. Does everybody see my slides well? Awesome,
yes.
Thank you so much. This is a paper that is not written yet, so it's on my desk and I'm supposed to write it soon. My co-authors Lucas and Marco are definitely pushing me to finish this, but it's been crazy. The title is still tentative: Testing Conflict Theory in the Field, a Field Experiment in Swimming Pools. This is something that I wanted to do for a long time. I wanted to do a study like this. I'm sure that most of you who are in this session, who are listening to this talk, you've probably been in the position, if you wrote a contest paper where you send it to a top journal, you send it to a good journal overall, and the referee would usually say, well, this is great, you know, as far as the results go. You know, you find these patterns of either overbidding or maybe some other things, some interesting phenomena, behavioral phenomena. But the question is, do they generalize to the, you know, kind of to the real world? So it's a question of external validity. And so that is why I sort of got into this idea of, well, how can we test the basic even the basic predictions from contest theory, from conflict, from tournaments in the field. And so this is what we came up with. But let me just give you a little introduction as far as the motivation goes. I think all of us, we would agree that conflicts are just an unavoidable part of our life, and people engage in conflict when they compete for resources, mates, promotions, you name it. The common characteristics of a conflict would be probably three parts. Again, there are different definitions that you will find in the literature, but these three things sort of define conflict. First one, it's a scarce resource. So you have to have a scarce resource that you're competing for. Second one, that there is a costly efforts that need to be exerted in order to get that resource. And third, and this one is kind of iffy, it's that there is no positive third-party externality. Okay, so the kind of labor tournaments or sports contests would probably not fall into this category of conflict and this particular definition, because in those instances, when you use a labor tournament, yes, you're competing against, when you're talking about the agents are competing against each other, but the higher competition would lead to benefit the principal, somebody who's employing the agents in order to produce good. And so there would be an external benefit from a higher level of competition. While when we talk about things like war, and other instances, you know, political lobbying and things like that, then in those instances, conflict doesn't have that external benefit, it just has a cost. So that's the famous sort of model of rent-seeking by Gordon Tullock, and that was his idea of rent-seeking in the first place. So there are some surveys that have been done. I've been a part of writing a lot of them too. So there are surveys on contests over bidding, on war and conflict. I'm not going to be doing extensive literature review. I do want to point out a couple things here, though, is that when you look at this literature, what you will find is the lab experiments support comparative static predictions. So basically, the idea is that on a grand scheme of things, and even today's talks have kind of highlighted that point, that if you have a theoretical model that basically gives you some predictions about the behavior, about the incentives in the contest, that model, and you bring it to the lab, you will not find the level of Nash equilibrium that will be, you know, you won't match the Nash equilibrium, but you will find the comparative statics. So for example, one of the famous comparative statics, probably one of the most essential ones, is in terms of the incentive effect. And that is that the effort or the competition increases when the value of the prize goes up. So if we have a tournament that has a higher value of the prize, you should expect people competing more for that prize. Another one is what we call the discouragement effect, or the idea is that the stronger contestants will exert higher effort than the weaker contestants. The weaker contestants get discouraged by the stronger contestants, so on and so forth. And so that's why there's many papers that would fit into these categories. But again, the general finding from the lab experiments is the support of these comparative static predictions. Now, when you look at the field studies that are trying to battle this question of external validity, so these studies, you know, in the lab are very well done, very well controlled. They have a great internal validity, but they do fall short when it comes to external validity and bringing this to the field. And so the field experiments, they have been done as far as the contests go, and there's a growing number of those experiments, but they usually study tournaments and contests as incentive mechanisms. So for example, how, you know, we use this mechanism, will the workers perform better at this particular workplace? You know, will people get better educational attainments? You know, will people, managers or salespeople will be selling more, so on and so forth. So the point is that the field experiments use or study tournaments as incentive mechanism, most of them at least. And so the research question that we had in mind was, how do economic agents behave in the conflict environment when there's no positive externalities from conflict? So basically, when we are truly in the conflict setting, it's not a tournament, it's not motivating workers, it's not doing this, it's just a conflict situation. And basically, do we still find those comparative statics? Does the theory predict behavior in a matter that will be supported by the data from the field. And so we look at particularly in the 3 dimensions, and that is, or the 3 comparative statics. One is the value of the price. As we increase the value of the price, do people fight more? The scarcity of the resource, and the strength of the contestants. So those are sort of key questions that we are interested in, or the key variables that we're going to be looking into. And the general question is, do the findings from the lab generalize to the field? And that's kind of what motivated this paper in the first place. Just to give you an idea of what we have in mind as far as the model, it's a simple model that in which you have 2 players that are competing for the prize value, V1 and V2. So they value the price differentially, they exert efforts, and the probability that player 1 wins is going to be proportional to the efforts that they put in. So here, player 1 puts E1, it's divided by E1 plus E2, and player 2 puts E2, it's going to be divided by E1 plus E2. You can then calculate the expected payoff, which is going to be the probability that you win times the value of the price minus the cost. Let's say it's a linear cost. It's the marginal cost is 1. It's just, again, this model is used as an just to provide us comparative statics. We don't care too much about point predictions in the first place. So when you solve this model for an equilibrium effort, you will get typical sort of expressions that will be the function of my value, your value, in a specific fashion. And so you will get the probability of winning in the equilibrium, which is going to be this expression that comes from the efforts that are calculated from the equilibrium. So you can calculate probability, and you get the comparative static predictions, and that is my probability of winning is going to decrease this is the probability of player 2. So your probability of winning is going to decrease in my value, and it's going to increase in your value. So that's sort of the main comparative static prediction from pretty much any model. You take any contest model with the reasonable assumptions, and they will generate this sort of a prediction, and that is, as my value goes up, your probability of winning is going to go down. As your value goes up, your probability of winning is going to go up. So the reason why I'm focusing here on the probability of winning, because it's going to be difficult for me to measure effort as such in the field, and instead I'll be able to measure the probability of how, or the outcome of the contest as such. And so that's why I'm going to focus, again, the theory kind of focuses on the probabilities here. Now to the experiment. So this is the main kind of idea of what we did. We went through a lot of tasks that we thought that could provide us with an interesting environment to study conflict, and we eventually converged on the swimming pools. There are quite a few reasons why we did that. Again, those of you who are interested will be able to read it in the paper. But again, swimming pools gave us a lot of desirable features that we needed for this particular experiment. So we chose 6 swimming pools in Brisbane, in Australia. We hired 4 actors who basically were students, and they were working they were pursuing their acting careers. So they have a little bit more experience than you and me probably. Acting, we had 2 males and 2 females. We wanted to see maybe there's a gender difference there. So we wanted just to have a balanced approach to this design. We approached 205 swimmers. These actors approached 205 swimmers in a span of 5 weeks. So we collected this data for 5 weeks in swimming pools. So what are the treatment variables? So we manipulated the value of the price for an actor. So the value of the price for player 1 right? So remember that value of the price is gonna impact the likelihood of you winning or player 2 winning. So we manipulated the high and low valuation message. In one instance, the actor would come to people who are swimming in the lane and they would say, excuse me, there is a race tomorrow and I really need to train for it. So do you mind moving to a different lane? So this is one of those studies where there was no race to follow up. So there was a level of deception that was involved in this particular study. We are not too concerned about this because, again, it's not a lab. It's a real world, and basically in this real world, there's no reputation to upkeep for our lab. So, and in this particular environment, this was a trade-off, a necessary trade-off that we had to follow. And we wanted to sort of have a race next kind of day, but then we realized there was just no way for us to feasibly do this, and so we stuck with this environment. And in the low valuation message, basically somebody would say, hey, excuse me, I need to train for a race. So there's just kind of a general excuse. There is a reason why you need to be swimming in that lane by yourself, but again, it's not as urgent. And again, the question would be, do you mind moving to a different lane? The scarcity of the resource, basically the way that we measured it is through a naturally occurring variation in the swimmer's valuation. So the idea here is that we had the number of people, we would measure how many people were in a swimming pool, how many people were in a lane that you get in. So a swimmer would get into the lane and you would know that there's one person swimming or two people swimming. And then you would know how many people are in the adjacent lane. So all of that was recorded by our RA at the moment of the collecting of that data. And also we recorded variables as far as the strength of the swimmer. We did that through recording approximately their height, their muscularity. We had actors and rate those people, how muscular they are, and objectively, more objective measures, we had a speed with which they were swimming. And this is something our array would record. So before choosing a lane to which they would send an actor, there was a sort of a measurement where they would take and they would measure approximate speed of the swimmer in that lane. So we knew how fast those swimmers were. So this is just sort of the instructions to the array. It's sort of small, but you can read it. We would record what time and date, what's the name of the swimming pool in which they went. We would ask them to check all the lanes that are active so we know which lanes are active. We would then ask to say to calculate how many people were in each of these lanes. Then we would ask to look for an active lane with the least number of swimmers in it before we would send our actors. The reason we did this sort of selection, because it wouldn't make sense for you to go to the most populated lane and then ask people to leave it, because you need to swim. You need to persuade pretty much, more people in the more populated lane. So instead, what we did, we would send them to the least populated lane and ask people to leave. But we definitely didn't want to have too many swimmers, so not more than 3 swimmers. If the swimming pool was too busy, we didn't collect data. Then we would measure the speed in that lane. And we would have the swimmer's speed would be measured. Then the array would then randomly select message 1 or message 2 that they would give it to the actor. And then they would record the actor's name. And then they would record the speed of that particular swimmer with which the actor interacted. Because remember, before they would record the speed of, let's say, 3 swimmers in that lane, but we really wanted to know what is the speed of that particular swimmer that our actor was interacting with. And so, and after that, we asked the, for the array to record some of the information. We also asked the actor to sort of pay attention to some features of the people that they were interacting with. The instructions for the actors were in a similar fashion, that we asked them to walk to array and ask which lane and message were selected for you. So the actor would come to array and say, well, which lane should I go to? Lane number 3. What message should I say? Same message 2. And then they would walk to the shallow end of the selected lane and wait until a swimmer would stop, and then they would jump into the lane and they would deliver one of the 2 messages. We wanted to have a very strict script here, and so we basically, if swimmer would not, if this, let's say, if there was, we kind of gave them a script to follow. So for example, if swimmer were to ask what kind of race it is, because that's kind of a question that is natural to pop up, they would say it is a UQ race, so the University of Queensland race. If the swimmer does not want to move or make other comments, then we would just ask our actors to say, well, I need to train, could you move? If the swimmer would say no, then we follow up with the next question. Okay, then can you tell me how much time will you need to finish your swim? We thought that that would be a good proxy. The more continuous proxy, it didn't work out. People would not respond or respond kind of categorically. And then we asked them to try to remember the exact interaction, because we recorded that interaction in a script. So we recorded those messages that they had. And we also asked them to pay attention to sort of characteristics of the swimmer, because we later on asked them to report those characteristics. How muscular that person is, at least on the scale that they can perceive, how tall you think they were. And so these were the race, whether they were native speaker or not. And so those were the questions that we wanted for the actors to pay attention to. Our hypotheses are straightforward. Again, there is nothing complicated here. The hypothesis 1 is that the probability that the swimmer leaves the lane is higher when the actor delivers a higher evaluation message. So that's when the V1 is greater, the probability the player 2 leaves should be greater. The probability that the swimmer leaves the lane is lower when the resource is more scarce. So the idea is that my valuation for this lane is pretty high, because if I were to move to this lane, other lanes are pretty busy. And so I'm going to be losing valuable resource. The hypothesis 3, the probability that the swimmer leaves the lane is lower when the swimmer is stronger. And this is kind of a weaker part of our study, because what does that mean that the other person is stronger? Is it a faster, taller, more muscular? So we have all of these that we try to answer. But the question is, again, will that pattern at least be observed in this setting? So our sample, you can see we had male actors, female actors balanced there, high valuation and low valuation message. The total was 205 swimmers that we approached. The number of swimmers in the lane on average was 1.4. The number of active lanes was about 6 out of 8. And number of people per active lane was about 2. So again, the 2, we would choose a smaller, less populated lanes on purpose. This is the gender and ethnicity breakdown for our sample. So the results, I'm going to kind of follow the same pattern: valuation, scarcity, and strength. So the result about the actor's valuation. So you find that 49% of swimmers leave the lane when the message indicates higher valuation, and only 35% when the message indicates lower evaluation. So basically, it looks like that the pattern is consistent with our main incentive hypothesis. So when the value of player 1 is higher, the likelihood that the player 2 will leave or lose the contest or conflict is going to be higher as well, or the probability of leaving is going to be higher. The next question, as far as the scarcity, so swimmers are significantly less willing to leave the lane when there are more swimmers in the adjacent lane? So I see the question. Okay, the question that I got on the chat, would it matter for the predictions whether the participants also had a race in the near future for which they were preparing versus not? I mean, it would, because that would be evaluation for player 2. It would actually matter. It would be great for us to know that, but it doesn't matter for us as much because of the random assignments. So our actors are randomly coming to different people. And so we would expect that, you know, the same people who have and do not have race on the other side, they sort of randomly assigned to treatment and control. But of course, that would be a great information to have. Unfortunately, we don't have that. We're already collecting a lot. We ask a lot of tasks from our arrays. Then the next, the two graphs here. So what we look here is the swimmers in adjacent lanes. So so swimmers are significantly less willing to leave the lane when there are more swimmers in adjacent lane. So look at this graph. This is the conditional upon the swimmer leaves and the swimmer stays. So this is our actor approaches the swimmer, and the swimmer, when the swimmer stays, that's the case when there are fewer people in that lane. The swimmers, when swimmer stays, let's go with the swimmer. Swimmer stays is right here. So the swimmer will stay if there are more people in adjacent lanes. So if there are 3 people in the next lane, then the swimmer will not leave. If there are 2 people in the adjacent lane, then the swimmer is more likely to leave, because they're like, well, I can be in this lane, or I can just simply jump to the next lane. I mean, in extreme case, if you think that, you know, the swimming pool was completely empty and somebody jumps in and asks you to move, it's not a big deal to move because you just go to another empty lane. So that's an extreme kind of a case. So another way to look at this is the swimmers in the lane minus the adjacent lane. So that's really the true measure of scarcity, of how much punishment you will, or how much reduction in your value you're going to experience if you were to move from this lane that has very few or fewer people, and you move to the next lane that has more people. So that's the difference between the two, but still you find the same response, that swimmers are significantly less willing to leave the lane when there are more swimmers in the adjacent lanes. Then the results on the strains are a little bit more difficult to interpret here, because again, what's being stronger in this sort of setting means? Was it muscularity and height? If that's the case, we don't find much of the difference. So whether the person decided to leave the lane or staying in the lane, the difference in muscularity really doesn't matter, or the difference in height really doesn't matter. We do find the results on the speed of swimming. So we find the faster swimmers are significantly less likely to leave the lane. So one interpretation would be those are the stronger players, and that's the strength test. Again, is that a really good proxy for it? I don't know, but this is the best proxy that we have. And so this is the result, that we do find that the faster swimmers are significantly less likely to leave the lane. When you throw this into a logic regression, when you have basically a probability of leaving the lane, and then you have a bunch of the dependent variables that we were just going through: message, adjacent lane, speed, muscular height. So pretty much the same results kind of hold on in this multivariate regression. The same goes when we use the adjacent minus current lanes. So there's just a different dependent variable, but pretty much we see the same pattern when we look overall. When we look at gender, the gender of the actors and the gender of the swimmers, we just don't find any differences. So the gender of the actor does not impact the likelihood that the swimmer leaves the lane. So there's no difference in a way. The gender competitiveness difference, or whatever you want to call this, and that also also the gender of the swimmer does not impact the likelihood that the swimmer leaves the lane. So it's not only that our actor's gender doesn't matter, it also doesn't matter whether that's a woman or a man that reacts to the actor's request. It's still, we still didn't find any evidence there. So in summary, do the findings from the lab generalize in the field? In our study, yes, they do. We find support for the same comparative statics that we find support in the lab, but now we replicate that in the field. How do economic agents react to various incentives in the conflict environment? Well, very much in line with the basic theoretical predictions. So this is all I have for you guys, and there's further stuff that we're being done. We also did a survey where we went back to these swimming pools and we asked questions instead of performing experiments. Surveys sort of collaborate all of our findings, but there's just more stuff that still needs to be done. Okay, so Tim, perhaps faster swimmers feel more entitled to the lane since they presumably go there more often. That's a good alternative. I cannot rule that out. Speed may also indicate that the swimmers has more experience in the swimming pool and therefore know how to deal with these conflicts, more experience in battle. That's a good, I mean, I like these comments a lot. We will, when we write the paper, we will include them as well. Please go ahead, other questions? Again, you will need to unmute yourself.
Roman, it definitely seems to me like your study here does a good job of looking at the external validity from these kind of studies from the lab to the field. One thing I would ask about though is, you want to frame this as sort of a contest theory result. It seems to me like a lot of the kind of results you're getting could also be explained by some kind of social preferences or other regarding preferences. You talk about the idea that if the other person really needs it, you're more willing to give it. That might be motivated by social preferences. And the other person, if it's really costly to you, you're less willing to give it up. That could also be just overwhelming social preferences.
Yeah, absolutely. So this is a good question. And so the way we deal with this to disentangle some of these issues is with the survey. So we actually went back to these same pools and we asked surveys of people, hey, what would you do in this hypothetical scenario? So first of all, what people do when they say, well, would you leave? 80% of people say that they would. And remember that on average, about 40% actually do. So they say one thing, but they do another. But the comparative statics is actually the same. So when we ask them, would you leave if there was an urgent request or less urgent, so they sort of respond in the same pattern, but the levels are off. And that's in that survey where we ask questions about this, would you perceive this environment as a conflict situation? Would you perceive this as a more social interaction? And so we're able to parse a little bit of that. And yeah, but that's a very good point. We are definitely well aware that there is also a big part of the social norms that plays and social preferences that play a role in our experiment. Very good. Other questions? One more question.
Yeah, I have one, Roman. First, I think I recognize the UQ swimming pool, my old stomping grounds, which is cool. But second, so this might be a little harder to do with today's climate, but I would be interested in something where it's less of a kind of avoiding conflict and more sort of competing as a result, where you have somebody that moves over a lane and then they suddenly start swimming a lot faster to try and beat the
right. So you're thinking in terms of kind of being able to really measure that effort, because now once you have that effort, that would be a much more better measure of conflict intensity. And I love that idea. We did think about that. We're definitely going to change the environment for that. There are a couple ideas that we have. Again, this is very new to us. This is new to the field as well, because You know, usually we don't study conflicts like this in the field. You cannot just simply go ahead and start a war. You know, it's just something that is much more difficult. Getting IRB approval for this stuff is not as easy, because it's not only you doing in the field, but also, you know, you're saying, hey, you know what, we're going to start conflicts. You know, what's the benefit to the people? Really none. You know, there's some risks, but the benefit to the society is that we're going to learn something about conflict. So it's just not such a simple, trivial thing to do, to ignite these conflicts and being able then to study how people behave in them. But that's a great idea, and we are on the way to test that in the future. Okay, well, thank you so much for your time. Thank you everyone who was in this session. I hope you're enjoying your ESA conference in this new format. It's been great to see you all, and at this time we will we'll conclude this session, and I hope to see you sometime in the future. Have a good one. Bye-bye.
It was good.
Thank you, everyone.